You hear the words time crystal and you think one thing: perpetual motion, free energy, something that breaks the laws of physics. You're wrong. A time crystal doesn't break any law. It does something stranger. It moves at the lowest possible energy state. It vibrates when it shouldn't be able to vibrate. And nobody believed in it for 5 years, until 2 laboratories built it. This is the story of an idea that survived being killed. Autumn 2010. MIT, a small office in the physics building. Frank Wilczek is preparing a lecture on symmetry. He won the Nobel Prize in 2004. Today he is just a professor with a notepad. On his desk, a small diamond. He picks it up. Diamonds are crystals. The reason a diamond is a diamond, and not just a smooth lump of carbon, is symmetry. The atoms inside arrange themselves in a perfect repeating pattern. Up, across, down. Up, across, down. Forever in 3 dimensions. Physicists call this breaking spatial symmetry. Empty space treats every direction the same. A diamond doesn't. The atoms have picked a structure. Wilczek is supposed to teach this. He has taught it many times. But today he asks a question he has not asked before. If atoms can break the symmetry of space, repeating in every direction forever, could atoms break the symmetry of time? Could there exist a kind of matter that, instead of repeating in space, repeats in time? A material that, in its lowest possible energy state, its ground state, vibrates forever? He writes it on a notepad. He calls it a time crystal. Within 2 years, he will publish the idea. Within 3 years, half the physics community will say it's impossible. Within 5 years, a no-go theorem will prove the idea cannot work. Within 7 years, 2 laboratories, independent of each other, will build one anyway. This video is the story of how that happened. February 2012. Wilczek and a colleague named Alfred Shapir published 2 papers on the same day. One is called Quantum Time Crystals. The other is Classical Time Crystals. Both argue the same thing. The reaction is immediate. Patrick Bruno, a physicist at the European Synchrotron in France, publishes a critique within a year. He says in Equilibrium Quantum Systems, the kind Wilczek is describing, time crystals are mathematically impossible. The very ground state Wilczek imagines doesn't allow it. Then in 2015, 2 physicists, Watanabe in Japan and Oshikawa, also in Japan, go further. They prove it as a theorem. No-go, a formal mathematical statement that says, as Wilczek originally defined it, the time crystal cannot exist. This is, for most ideas in physics, the end of the story. A Nobel laureate had a wrong intuition. He'll move on. Wilczek doesn't move on. He continues to think about it. He writes about it in essays. He gives talks. He insists, gently, that the idea has merit, that the intuition is right, even if the formalism needs to be repaired. In 2016, 4 physicists at Princeton, Vedi Kahemani, Achilles Lazarais, Radharish Moisner, and Shivaji Sundhi, propose a fix. They suggest, forget equilibrium. What if a time crystal exists in a driven non-equilibrium system? A system that is being constantly tickled by external forces. In that case, they argue, the no-go theorem doesn't apply. A time crystal might be possible. The physics community is skeptical, but the question is reopened. Now, somebody just needs to build one. March 2017. 2 laboratories on opposite sides of America publish results in Nature the same week. In Maryland, Christopher Monroe leads a team using trapped ytterbium ions. They use lasers to hold 10 ions in a perfect line, suspended in vacuum. Then they hit the ions with laser pulses at a regular rhythm, say, every 1 millisecond. What they observe is strange. The ions don't oscillate at the rhythm of the lasers. They oscillate at half the rhythm. A pulse hits at 1 millisecond, 2 milliseconds, 3 milliseconds, but the ions only respond at 2 milliseconds, 4 milliseconds, 6 milliseconds. This is the mathematical signature of a discrete time crystal. The system has chosen its own period, slower than the drive that powers it. In Harvard, Mikhail Lukin's team does something different but related. They use nitrogen vacancy centers in diamond crystals. These are tiny defects, places where a nitrogen atom has replaced a carbon atom and an adjacent carbon atom is missing. Each defect has a quantum spin. Lukin's team can apply microwave pulses to these spins. What they observe is the same signature. The spins oscillate at half the drive frequency. The irony is exquisite. Wilczek had his idea looking at a diamond. Lukin builds the proof using actual diamonds. When Wilczek hears, he does something Nobel laureates rarely do publicly. He laughs. 2 laboratories, working independently, just built something that the no-go theorem said was impossible. The catch: they built the modified version, the driven non-equilibrium discrete time crystal that Imani's team had proposed in 2016. But they built it. The atoms vibrated. The crystal was real. A new phase of matter had just been added to physics. Let me try to give you the right intuition for what a time crystal is, because most people get it wrong. A regular crystal, like a diamond, like quartz, like ice, breaks the symmetry of space. Empty space is the same in every direction. But the atoms inside a crystal are not. They've arranged themselves in a repeating pattern. Up here, to the right of that one. Down. Up. Repeat. Forever. This is the strange thing. Physicists tell their students every year. A crystal exists because something is broken. The symmetry of space. If empty space is a blank slate, where every direction is equivalent, the crystal has carved a structure into it. A time crystal does the same thing, but for time. Empty time, like empty space, is symmetric. If you ask a system at this instant what it's doing, and you ask it again 1 second later, a system in equilibrium gives you the same answer. The laws of physics don't prefer one moment over another, but a time crystal does prefer. It gives different answers at different moments, in a regular repeating pattern, like a heartbeat, like a metronome. And here is the part that confuses everyone. It does this in its ground state, the lowest possible energy, the state where there is, technically, no extra energy left to fuel motion. This is why people think it violates conservation of energy. It doesn't. The crystal isn't generating energy. It isn't doing work. It's just repeating. The way a regular crystal repeats in space without violating any law. A time crystal repeats in time without violating any law. The repetition is not a consumption of energy. It is a property of the structure. A diamond doesn't run out of diamondness. A time crystal doesn't run out of beat. After 2017, time crystal research accelerates. In 2021, Google uses its Sycamore quantum computer, a 53-qubit processor, to engineer a time crystal directly inside their machine, not in a vacuum chamber, not in a diamond, in a quantum computer. For the first time, time crystal physics becomes accessible to anyone who has access to a quantum cloud service. In 2022, a team at the University of Hamburg, led by Andreas Hemmerich, builds the first continuous time crystal. This one is closer to Wilczek's original dream, not driven by external pulses at a fixed rhythm, but generating its own internal frequency, a truly self-sustaining oscillation, built from a Bose-Einstein condensate inside a laser cavity. Then, in 2024, a paper appears in Nature Physics. A research team observes a time crystal in a Rydberg gas at room temperature. Stop. Think about that. Until 2024, Every time crystal experiment required temperatures near absolute zero, colder than deep space, colder than anywhere humans normally work, 10 degrees above 0 Kelvin, 5/100ths of a degree. Now, room temperature, the temperature of your kitchen. Time crystals have moved from physics curiosity that requires $1 million refrigerator to phenomenon you could potentially put in a chip. This is the threshold beyond which technology becomes possible. October 2025, University of Chinese Academy of Sciences, a research team led by Wenjie Liu, publishes a paper that nobody quite saw coming. They take a 36-qubit quantum computer and try to maintain something called a GHZ state, Greenberger-Horn-Zeilinger state. It is one of the most fragile, most useful entangled states in quantum computing. If you can keep 36 qubits in a GHZ state, you can do things in 10 seconds that classical computers would take centuries to do. The problem: GHZ states fall apart in microseconds. Decoherence, interaction with the environment, destroys them. Liu's team adds a time crystal to the system. They use the time crystalline phase as what they call a safe house, a stable rhythmic structure that protects the GHZ state from decoherence. The GHZ state lasts longer. This is, as far as we know, the first practical use of a time crystal, not a curiosity, not a demonstration, a working component of a quantum computing system. What time crystals offer is a kind of memory that doesn't forget, because the configuration keeps repeating. The system, in some real sense, never loses its initial state. It refreshes itself every cycle, forever. Quantum memory that never forgets. Frequency standards that never drift. Precision clocks that synchronize entire processors. These are the applications that researchers in 2026 are actively working on. The thing Wilczek imagined in his MIT office in 2010, the crystal that breaks time, might be how the quantum computers of 2030 remember. Here's what I want to leave with you. When Wilczek had his idea in 2010, he wasn't trying to invent a new technology. He was trying to complete a piece of physics. Symmetry, the most beautiful concept in physics, the thing Einstein loved, applies to space and time equally. Crystals broke spatial symmetry. Some kind of matter, surely, must break temporal symmetry. The hole in the picture had to be filled. He didn't know what filling it would do. Nobody did. 13 years later, the answer is starting to come in. Time crystals might be the memory of quantum computers. They might be the heartbeat of precision clocks. They might be a phase of matter we use in technology that doesn't yet exist. This is how science works, not the science of textbooks. Applications first, theory second, the real science. Somebody asks a question because the question is beautiful. The question seems impossible. The community pushes back. After a decade of work, the question turns out to have a rich answer, and the answer turns out to matter. The diamond on Wilczek's desk has not changed. It is still just carbon arranged in space. But because of that diamond, we now know carbon, or anything else, can also be arranged in time. In 10 years, you may walk into a store and buy a quantum device. The chip inside it will hold information for hours, days, years. Because somewhere in the chip, a tiny crystal is beating, forever, without a heart, without a battery, without consuming anything. Just because somebody once asked if it was possible in a laboratory in Helsinki, Finland in 2026, a team is looking at signatures of something they cannot quite explain. It is not a time crystal. The math is wrong. The rhythm is wrong. The temperature is wrong. It might be a space-time crystal, a phase of matter that breaks the symmetry of both space and time at once. Theorists have predicted this might exist. Nobody has seen it. If they confirm it, it would be the first new phase of matter since time crystals were verified in 2017. The question is, What does it mean to break two symmetries at once? That is the next story.